next example is verify mean value theorem for the function fx is equal to 1 by x square and gx is equal to 1 by x on the interval closed interval AB. So we are given the two functions f and g, and you have to verify mean value theorem means you have to verify the Cauchy's mean value theorem. If the question is verify mean value theorem and if only one function is given, then we have to verify Lagrange's mean value theorem. Here we have to verify mean value theorem, but the two functions are given f and g. So we have to verify the Lagrange, verify the Cauchy's mean value theorem. Also show that the point C is the harmonic mean between, this is the short form h dot m dot, harmonic mean between A and B. That is, what is the harmonic mean of between A and B? 2 times AB divided by A plus B is called harmonic mean between A and B. So we have to show the value of C. C is the harmonic mean, means we have to show the C value of C is what? 2AB divided by A plus B. So fx is 1 by x square and gx is 1 by x. So their derivatives f dash x is what? 1 by x square means x raised to minus 2, and the derivative of x raised to minus 2 by x raised to n rule is minus 2 x raised to minus n minus 1. That is minus 2 minus 1 is minus 2. And g dash x, don't write g dash x is minus 1 by x square, derivative of 1 by x. So it is minus 2 by x cube, derivative of shift this x raised to minus 3. So we have minus 2 by x cube. Clearly, the function fx and gx are continuous on closed interval AB and differentiable on open interval AB. Because these fx and gx are the polynomial functions and are continuous and differentiable everywhere. So don't prove this statement, that just write in every example of Rolle's theorem, Lagrange's mean value theorem, Cauchy's mean value theorem. This statement is obvious, or directly write that clearly or obviously the functions fx and gx are continuous on closed interval AB, because the interval is closed interval AB, and differentiable on open interval AB. So in Cauchy's mean value theorem there are two conditions. In the Lagrange's mean value there are two conditions. What are the conditions? That the functions are continuous on closed interval and variable on open interval. So this is the Cauchy's mean value theorem. So in the Cauchy's mean value theorem, the function f and g are continuous on closed interval AB, differentiable on open interval. These are the only conditions. The third condition is what? G dash x is not equal to 0. So in the Cauchy's mean value theorem, there are three conditions. Okay. So this condition is in order to prove this GB minus GA is not equal to 0. So also in the Lagrange's mean value theorem there are only two conditions: continuous on closed interval, differentiable on open interval. So in order to verify Cauchy's mean value theorem, just state that the functions are continuous on closed interval AB or the interval given in that example, and show them, and say that the function is differentiable on open interval AB. So this is the Cauchy's mean value theorem. So the problems. Fx and gx, the two functions are given. In this example, there are two functions. So find their derivative f dash right here, f dash x, g dash x. Then by Cauchy's mean value theorem, there exists at least one point C belongs to open interval AB such that f dash c divided by g dash c is equal to f of b minus f of a divided by g of b minus g of a. Okay. So this is the Cauchy's mean value theorem. F dash c divided by g dash c is f of b minus f of a divided. Now we have to solve this example equation, and we have to find the value of c. So what is f dash c? F dash x is this. So just substitute x as c. So we have minus 2 by c cube, and then this is g dash x. So just substitute x as c. So we have minus 1 by c square. F of x is this 1 by x square. So f of b is 1 by b square. F of a is 1 by a square. G of x is 1 by x, so g of b is 1 by b minus this minus saying g of a is 1 by a. So simplify this. So this is minus minus become plus 2 by x cube. 1 by c square means into c square is equal to take a square b into b square as LCM. So we have a square minus b square as numerator, and take a into b as LCM. So a minus b as the numerator, and then a square minus b square simplification is a minus b into a plus b factorization. A square minus a square into b square divided by a minus b. Uh, a by b, that is into this divide means into uh, a ab divided by a minus b, and then a minus b and a minus b get cancelled. So we have a plus b divided by, and a out of this a square b square, one a and one b get cancelled to this. So we have a plus b divided by a into b. This is the value of 2 by c. This is 2 by c cube by into c square is 2 by c. And so 1 by c is what shift this to. And then c is what? Take the reciprocal, that is 2ab divided by a plus b. That is c is the harmonic mean between a and b. This question of this answer. Show that c is the harmonic mean between a and b. Therefore, this indicates we have c is equal to 2 times ab divided by a plus b, means c is the harmonic mean between a and b. And note that this c is 2 times ab divided by a plus b belongs to open interval ab, and therefore we say Cauchy's mean value theorem is verified. The next example is again on the Cauchy's mean value theorem. Verify Cauchy's mean value theorem. Fx for if the function fx is equal to e raised to x and gx is e raised to minus x, and show that c is the arithmetic mean on the interval ab. C is the arithmetic mean on the interval ab. So if in Cauchy's mean value theorem, the same question in another format. If in the Cauchy's mean value theorem, fx is e raised to x and gx is e raised to minus x, then show that c is the arithmetic mean a dot m dot on the interval, closed interval ab. Okay, so we have to show that c is a plus b by 2, arithmetic mean between a and b. So fx is root x and gx is 1 by root x, then show that c is the geometric mean. Okay, if fx is x square and gx is x, then show that c is the arithmetic mean. If x is sin x and gx is cos x, then show that c is the arithmetic mean. So these are the problems for homework. Verify Lagrange's mean value theorem. Fx is x minus 1, x minus 2, x minus 3 on closed interval 0, 4. Fx is tan inverse x on closed interval 0, 1. Fx is x square minus 3x minus 1 on this interval minus 11 by 7, 13 by 7. Solve all these examples. So these are some more examples. We'll see the proof of these examples. So solve all these examples. Fx is root x, gx is 1 by root x, like this. So solve. We have the value of c as the arithmetic mean, means a plus b by 2. Then 1 by fx is root x, geometric mean, that is c is root ab. We have c is root ab. In this example number 2, we have c is root ab, that is c is the geometric mean between a and b. So here fx is x square, gx is x. Then solve this by using this method. We have c is the arithmetic mean, means we have c is a plus b by 2. So similarly, these are the some examples on Lagrange's mean value theorem. Solve all these examples in your assignment notebook. Solve all these examples in your assignment notebook. There are also the problems on the Rolle's theorem for homework. So these are the problems for homework on Rolle's theorem. So solve all these problems of Rolle's theorem, Lagrange's mean value theorem, and Cauchy's mean value theorem, and communicate or send these answers of these problems through WhatsApp. So next topic is what? If, next example, if a is greater than 1 and b is greater than 1, B is greater than A, then prove that B minus A divided by root 1 minus A square is strictly less than sin inverse B minus sin inverse A is strictly less than B minus A divided by root 1 minus B square. And the second problem is for assignment. B minus A divided by 1 plus prove that is tan inverse B minus tan inverse A. Okay, this is the answer of the first problem. So let fx is sin inverse x. In this second example, we define fx as tan inverse x. So in this example, define fx as sin inverse x. And then f dash x is 1 by root 1 minus x square, the derivative of sin inverse x. In the second example, fx is tan inverse x and its derivative is what? 1 by 1 plus x square. Then by Lagrange's mean value theorem, f dash c is what? F of b minus f of a divided by b minus a. Actually, these are the examples on Lagrange's mean value theorem. So by Lagrange's mean value theorem, f dash c is f of b minus f of a divided by b minus a, where c belongs to polynomial a. Then what is f dash c? F dash c is 1 by root 1 minus c square. F of b is what? Sin inverse b. F of a is sin inverse x divided by b minus a. And then we have shift this b minus a to LHS. B minus a divided by root 1 minus c square is equal to sin inverse b minus sin inverse a. As a is less than c, strictly less than b, because c belongs to open interval a b, means what? C lies between a and b. C is strictly less than b and c is strictly greater than b, lies between a and b. Then a square is strictly less than c square is less than b square, because all these a, b are greater than 1 means all positive quantities, and therefore their squares, we have the same relation, that is less than in between their squares. If the a and c are negative, then after squaring we have the greater than sign in the place of less than. But here a, b, c are positive, and therefore we have this sign remains as it is, that is less than remains less than. A square is less than c square, c square is less than b square. Then minus a square, that is applying negative on this. So we have minus a square. Now this less than become greater than. Minus a square is greater than minus c square is greater than b minus b square. Okay. Then add 1. So this greater than remains as greater than. Add 1 plus, that is 1 minus a square, 1 minus c square, 1 minus b square. Then take a reciprocal of all. So 1 minus 1 by a square is less than, now greater than becomes less than. If you take reciprocal, then we have greater than. If there is sign greater than, then it becomes less than. And if there is sign less than, then it becomes greater than. But there is sign greater than, so it becomes less than after taking reciprocal. 1 by 1 minus c square is less, now is greater than converted to less than 1 by 1 minus b square. Then taking square root of all, this root 1 minus a square is less than root 1 minus a square is less than root 1 minus b square. Okay, take root of all quantity. Okay, so don't write this step, take root of, we have this, don't write both these steps. So after taking root, we have root 1 by root 1 minus a square is less than root 1 minus b square is less than root 1 minus c square. So before this step, don't write this step as well as this step. So after this step, write this step. That is taking root. After 1 minus a square greater than 1 minus c square greater than 1 minus b square, don't write this step. Write this step. That is take root. So what do we have? Root 1 minus a square is greater than root 1 minus c square is greater than 1 minus b square. So after taking root, we have the same sign, greater than remains greater than. Then taking reciprocals of all these sides. So 1 by root 1 minus a square. So now this greater than becomes less than. Root 1 by root 1 minus a square less than 1 by root 1 minus. So don't write this step. After this step, write this step. That is taking root of all quantities and then take reciprocal. So greater than becomes less than. And then multiplying by b minus a throughout. So less than remains less than, because this b minus a is quantity, positive quantity. B is greater than a means b minus a is positive quantity. And if we multiply by positive quantity, then less than remains less than, greater than remains greater than. So after multiplying b minus a, we have this. And then b minus a divided by root 1 minus c square is what? this value is sin inverse B minus sin inverse A. So right, it is equal to sin inverse B minus sin inverse A. And then we have this. That is you have to prove sin inverse B minus sin inverse A is less than B minus A by root 1 minus B square, greater than B minus A divided by root 1 minus A square. So in the same, by using same method, we solve this example number 2. So next is the definition of increasing function and decreasing function. The function is called increasing if x1 is less than x2, implies f of x1 is also less than or equal to x2, f of x2. That is less than sign remains less than. Then the function is called an increasing function, and if less than becomes greater than or equal to, then the function is called decreasing function. And the function fx is called decreasing function if x1 is less than x2, implies f of x1 is greater than or equal to f of x2. Then function is called a decreasing function. So if less than remains less than, then function is increasing. If less than becomes greater than, then function is called decreasing. So fx is equal to this function x square plus 2 is increasing function, because what we have, 1 is strictly less than 2. And what is f of 1? F of 1 is 1 square plus 2 means 3. And what is f of 2? 2 square, 4 plus 2, 6. And we have that f of 1 is less than f of 2. And then so this function is increasing, or we say it is strictly increasing. When we say the function is strictly increasing, if x1 is less than x2, strictly less than x2, implies f of x1 is strictly less than f of x2, then we say the function is strictly increasing. And the function is called strictly decreasing if x1 is less than x2, implies f of x1 is strictly greater than f of x2. So this function x square plus 2 is strictly increasing function, or say it is increasing function. Then f of x is equal to minus x. This function is a decreasing function. 1 is strictly less than 2, but what we have, f of 1? F of 1 is minus 1. And f of 2 is what? Is minus 2. And we know that minus 1 is greater than minus 2. So f of 1 is greater than f of 2. So less than sign becomes greater than, and therefore this fx is equal to minus x is decreasing function, or is strictly decreasing function. So these are the definition of increasing function and decreasing function. Then the statement of this theorem is number 1 is what? Let fx be a function continuous and differentiable on open interval ab, and f dash x is greater than 0 for all x belongs to ab. Then fx is strictly increasing function in the closed interval ab. So this is the another format to show the function is increasing function or a strictly increasing function. So when we say the function is strictly increasing, if the derivative of the function is greater than 0 for all the points lies in that interval, f dash x is greater than 0 for all x belongs to open interval ab. So this is the another format of the definition. This is the replacement to show the function. By using this, we can show the function is increasing, or either by using this theorem, we can show the function is increasing. That is, just show f dash x, find its derivative, and show f dash x is greater than 0 for all x belongs to that open interval ab. Then we say the function is strictly increasing in the interval, closed interval ab. And the function is, if the function fx is continuous and differentiable on open interval ab, and if f dash x is less than 0 for all x belongs to open interval ab, then fx is called strictly decreasing, or just say decreasing function on closed interval ab. So this is the another format of definition of the decreasing function, or another way to how to show the function is increasing and function is decreasing. So we can show the function is increasing by using finding its derivative and value at the point. So f dash x is greater than 0, f dash x is less than 0. Then the point where f dash x is exactly 0 is called stationary point or critical point, or point of relative extrema. So if the function, the derivative of the function is greater than 0, then function is increasing. If the derivative of the function is less than 0, then function is decreasing. And if the derivative of the function is 0 at the point, then such a point is called stationary point or critical point or point of relative extrema. So These are the definitions of the decreasing function and increasing function. Examples on the decreasing function and increasing function we will see in the next lecture.